Yes, sir.
Kirtana, can you hear me?
Yes, sir.
Okay, so today I'll be discussing about magnetic field due to moving charge. Okay, basically we have studied earlier that due to the motion of charges, we can produce magnetic field. Right? Now we'll see how it works. So first we'll be discussing about magnetic field due to moving charge. Then we will talk about Biot Savart Law. Okay, these two things are the topic of discussion for the today's class. Yes, so um, yeah, let me know. Can you see the screen? Krishna, can you see the screen? Start discussion. Uh, Magnetic field due to. So basically, if charge is static, produces what? Electric field. Okay, but in motion, uniform. Okay, uniform motion can produce magnetic field. Okay, these two things are the discussion. So if this is the case, let's see how it actually works. Mm, Magnetic field. Okay, so we'll be discussing about this thing. So assume we have a charged particle plus Q. This particle have a velocity. Okay, it has some velocity v. One thing remember, Kirtana, whatever we are discussing right now, it is an experimental experiment. Okay, we can't have derivation for every second thing. So this is one thing you have to keep in mind. And yes, let's see now. Okay, yeah. So this is the thing you have a charged particle over here. Let's make it positive. Q. It is moving with some velocity v. Okay, so Kirtana, if this is moving in this direction, this will be its line of motion, right? This is going to be its line of motion. Basically, this is the line on which it is moving. So maybe let's treat it in this. This is its line of motion. And right now, assume the magnetic field to be zero. Magnetic field is zero on line of motion. So assume Kirtana, I'm going to take a distance r. So assume this is your distance r. Okay, at here, somewhere here. So this is your r vector, this is your v vector. And we said this is a line of motion and we don't have any magnetic field over there. Okay? So what is the angle right now? If I ask you what is the angle between v and r, so Kirtana, hello. Yeah, if you can see carefully, I was saying that on this line of motion, if you are going to calculate your magnetic field, you can say that your magnetic field is coming out to be zero. So it means if the angle between, look, whatever we are discussing right now, it is an experimental thing. Okay, we can't do a derivation right now. The angle between V and R, if it is zero, then magnetic field is zero. Okay, this is one experimental thing we had. It means either way also, right? If it is 0 degree or 180 degree, either case. Okay, two, three. Okay. After this, assume that I have another distance, maybe this. If I'm going to take this r, and if I say this is theta, if theta between v and r is not equal to zero, means it has some value, then at this point the magnetic field is going to be inwards. Okay, it is going to be outward basically. Outward. This point represents outwards of plane. Thirdly, it is different line. I'm just trying to make it inwards. And look, what we have discussed so far is I had a charge, okay. Then we did some experiment and we tried to calculate magnetic field. So what I did is when I was calculating magnetic field on the line of motion because it is moving in this line. And when I tried to calculate motion, magnetic field on the line of motion, I got it zero. Okay? So we said, okay, if the charge is moving and if we are going to calculate on the line of motion, we are going to do zero. Then we have more sides, right? We try to calculate and this side of the plane, at this side and this side. So when we did, we had some value here. B was not equal to zero. Here also B is not equal. Also, this inward and outward is basically the direction of magnetic field. Mean to say, velocity is in this plane, current plane where we are looking at. Okay, it's like this thing. This, if I wanted to make it more clear, this is like velocity going on. This is your distance, basically this r distance, and this is your velocity. Maybe this. Okay. Then this is your radius r. This angle theta. And when I'm saying inward and outward, it means either this thing is perpendicular to the particular plane or it is quadrant. Okay. This is what we mean when we are saying it is either going inside or outside. Is it clear now? And this is on this particular plane. Okay. Is it clear, Shreya? Is it clear,
Mhm.
Kirtana?
Yes, sir.
Okay. I was looking, if you look from top view, okay, assume this is the top view, okay, this is your eyesight. So what you will see, this is coming outwards, right? So we are saying this is outwards. This outward is represented by a point because it will look like it is coming towards you. So this is outward. It means it is coming towards you. If you look Assume if this is not here, okay, this line is not here, what you are going to see? You are only going to see this particular point. Okay, this is so when you look it from the top, what you see that this is going inside. Inside we put a cross. Is it clear how we are representing the sign conventions?
Yes, sir.
Okay, that is one thing. So you might have got a little bit idea about the thing. Now, if you see carefully, I have two parameters, okay? And what you noticed is my final parameter, which I am going to get, is dependent upon this angle theta, right? Can I say this? And this is
Yes.
perpendicular also. So if I try to bring a relation, I know that is my magnetic field. Okay, this magnetic field directly depends upon the values, right? Because more the value of the charge, more the value will be there. Okay, it depends upon Q also, it depends upon V also, it depends upon R also. But if you see, this Q is only participating in magnitude value, right? It does not participating in the angle, but angle depends in between them. So can I say I will take some function of theta, basically some function of theta depend upon, right? Can I say this?
Yes, sir.
Okay. So you know one thing that this B is actually perpendicular to both of the things. Do you could you remember any function which whose participation of two parameters led to third parameter which is perpendicular to each other? Could you think of it something sine theta? If I call this as sine theta, okay, VR times of sine theta, and I may be writing it as V cross R because you know the cross product is always perpendicular. Because if something, if something, if something is perpendicular to the both parameters, then this parameter must be result of their cross product. Understand my point?
Yes, sir.
Yeah. So you can say these two parameters, this B is result of okay, theta. So this B is equals to Q V R sine theta. Okay, R times of sine theta. Now you can more write it in the vector form. It can be written as Q R cross. This is the value clear of your charge. How it works like that? It's like charge is there. Yeah. So if this is going this way, this is going this way. By right hand thumb rule, what is the right hand thumb rule? Keep your right hand. Okay. Uh, Here we are going from. Assume this is R, this is V. We are going from R to V. Means you curl your hands in this way. Okay. Maybe your fingers should be like this, thumbs pointing upside. This should be thumb. These should be your fingers. These fingers are pointing toward the first vector. Maybe we are, if assume that right now we are doing R cross V. Okay. I'm just helping you how to remember the direction of the final product. Okay. So this is the first parameter. Your fingers should be pointing towards this. Okay. Now you can say your fingers are placed like this. Okay. Now you are going from R properly. It means now curl your this. When you are keeping when you are going to keep your hand like this, your thumb is going to point upside, right? So this point is showing the direction of the third vector. Is it clear?
Yes,
Because
sir.
perpendicular to both can either be upside also, can either be downside also. So which is it? Now assume that in this particular case, I am saying do a V cross R. So in this V cross R, if you are going to do like this, what will happen over here? You have to take a complete turn. No, we have to take the smaller turn. It means you just turn your hands downside. It means like this, and your hand is down. So now you can come up in this way. Now this is pointing downside. Okay, this is how you have to look the direction. But in this case, what is our main formula? Our main formula is R cross. Is it clear? So you have to take your hands towards this R, turn it up to V. Whatever the thumb is pointing, that is the direction of. Is it clear now?
Yes, sir.
On paper, how you are going to represent? Assume that this is your V, okay, and this is your R. These are in right now this particular 2D plane, okay, in the screen. Now this is your V vector. This is your R vector. So how you are going to represent it?
Between V and R.
What Kirtana? Yeah, I'm just saying it's a general formula.
Between V and R.
Yeah, between V and phi. Okay. What we are calculating actually, Kirtana, actually we did a small mistake. Whatever we were doing this formula, this is for the sorry, method is quite same, but incorrection is there. I will change it. Whatever I did, this is for the force. Okay. Force. This formula is basically force on a moving charge. This formula is for the force on a moving charge. 2VR. I'll just switch it back. Till here, you have to keep it as it is. Yeah, let's go back to our derivation form. But what we are saying is B is directly proportional to your theta. Make it as it is. B is directly proportional to your theta. B is directly proportional to the value of it. B was directly proportional to V, basically whatever the velocity is there. And B is also directly proportional, inversely proportional to distance, right? More the distance, basically, assume your charge is right now moving over it. And right now your distance is this and another distance is this. You directly know that more the distance, lesser the value, right? So this is a relation we can have. If you just go and combine all of them, what you're going to get is B is directly proportional to something. Okay. What is that something? You can call this as QV divided by R square and this theta. And you know because the value is basically perpendicular, right? So you can keep it as sine theta. Okay, clear? Why we are keeping it? Because we know the third parameter which is coming out, it is the result of this result is basically in the perpendicular direction. So we know directly if this is the thing, it must be this cross product of something, and cross product must be coming out of the sine theta. So Kirtana, very simple. If there is this proportionality sign, we are supposed to remove it, right? So in that case, we are going to put a constant. That is the value of that constant is mu naught divided by 4 pi qv sine theta divided by r. Um, and you might have clear with this constant till now. Right? If you could remember, in electricity, the constant k is basically 1 by 4 pi epsilon naught. Here, my constant is 1 by 4 pi as it is. But instead, epsilon, we have mu naught, and mu naught is not in the bottom, it is on the top. The only difference is there. Here, we had a whole value as, what is the whole value? 9 into 10 to
No.
the power 9. Here, the whole value is 10 to the power minus 6. Is it clear now? Okay.
Yes.
And you already know this this particular constant we have seen earlier also, right? If you see carefully, Ketna, I don't have any R to make a cross product because charge is a scalar value and you can't do a scalar product. Okay? So what you will do, just multiply up and down. If you do so, Q is as it is, what you can do now, V cross R divided by, because you have multiplied up and down with R and finally you've got R. Okay? That is the formula. It should be, even in the force formula, it should be Q V, and which can be written as Q V cross R. It is not R cross V. Okay? So, Krishna, what I wanted to say is, now you have a positive charge. It is trying to move in this direction. Let's come up in a normal plane. Okay? I'm talking about this particular plane. Because look, in this chapter, we will be discussing about three planes, right? My one velocity may be there, radius will be there, and third direction, how I'm going to represent the third direction. So that's why we come up with a convention cross dot. Dot means outwards of particular of this plane, inverse of this plane. Okay. Yeah.
Yes.
So assume I have this as velocity and this as radius. Okay. Can you tell me what is the direction of this magnetic field? Okay, I don't want the value, just get me the direction.
What is between V and R?
What happened it now?
It's between V and R.
No, no. I'm just saying what is the direction of it? What is the direction of magnetic field which will be coming due to this V and R? Angle between them is assume the theta, random theta. Just check it once.
Is it outwards?
Is it outwards of the plane, right? Okay, next. It is outwards. So what is the sign convention I need to make? This point. Okay? It is saying that outward. Clear?
Yes.
And where it is outward? Here. Here it is outward of the plane. Okay?
Yes.
All right. This is interesting. Okay, so Pita, in this particular figure, can you try to figure out what should be the angle between your magnetic field and your electric field? Kirtana, can you hear me?
Yes.
Yeah. What should be the angle between electric field? Because look, when charge was static, you had some electric field, right? Assume I started moving the charge. Can you tell me what will be the value? What is the direction of electric field, and what is the angle between electric field and this magnetic field, whatever generated by this case?
Are the perpendicular?
You can't say because very simple is if the charge is there, simply charge, okay, it will be having electric field direction all the directions. No, it won't have just one direction. So actually you can't define this. Okay. Because one side the field has some angle, another side the field some have angle. One side will be there which is parallel to that. Okay, so you can't justify this. That's why we are not considering about electric field when the charge is moving. Okay, we are only saying magnetic field when the charge is moving. Okay, that is.
Yes.
Okay, now assume that this is your V, this is your R. What do you think? What should be the direction of your magnetic field?
Inwards.
Inwards, right? Makes sense. So I think we can move to the next thing. Perpendicular to V. This is an important point. Remember this. Okay. And V is perpendicular plane which contains V and R. Okay. It's in another video if I wanted to explain this part. I'll just take the line over here. If you see carefully, this is one plane we have. Okay. Some diagram we have made over here. This will help us representing the plane. If you see here now, this is representing a 3D cube, right? If you see carefully the whole thing. Now what happens is, what will happen is, when I was saying that the line containing this and this, it means that when I was talking about, is it quite, yes. So assume this is a velocity vector. Okay, there is a charge which is moving in this particular region. Okay, this is a charge. Okay, and it has a velocity like this in this plane, and there is a, okay, and I am calculating the velocity at here. It means this is charge is right now here, velocity is in this direction, and charge in this plane. Okay, charge is in charge. The distance is this plane. So when I'm saying the velocity will be in the third plane, it means can I do it better? No, something like this. So here your velocity will be in the upper plane, pointing in this particular plane. Now this magnetic field is currently lying in this particular plane, the vertical plane. Where is your this velocity and this radius vector was present in this particular plane. Is it clear now the plane thing?
Yes.
So yeah, if I just get Okay, yes. Okay, fine. So let's talk about, because we have studied how a moving charge creates a magnetic field, right? Now we'll be discussing magnetic field due to current carrying wire. Due to current carrying wire. Okay. Whatever we are going to do, that is also represented by using Biot Savart Law. Okay. That is it. So assume I am having a very random wire. The current is I. Okay. What I'm going what I'm going to do is, let's say current is this. What I'm going to do is, let's say this is the reason. Okay. And this small length is basically DL. This small length is DL vector. This smaller element is known as DL vector. Now, from this particular angle, I am going to some distance from here. I am going to talk about this distance. Okay? This you can call as R vector. And this is the point. What I am going to do is I am going to calculate magnetic field at this particular point. Okay? Can you tell me, Ketna, if my in this particular case, what should be the direction of magnetic field? We will now we are going to calculate the value by using the formula. But can you think of what should be the ideal direction of magnetic field? I'm just asking the direction of magnetic field in this figure. Can you figure it out?
No, sir.
Why? Uh, can you assume one thing, that what is current? Current is nothing but
B.
motion of negative charges, right? Can I say it is due to the motion of negative charges electron?
Yes.
If my electrons, because current is going this way, can I say my electrons are moving in this direction? Can I say
Yes.
that?
Yes.
And you know one thing, my B
Mm.
was dependent upon the Q. It means if due to positive charge, I was getting direction as this, can I say due to negative, my direction should be this? Can I
Yes.
say? Okay. Just do one thing. Calculate the direction by assuming it to be positive. If assume positive charge is going this way, okay. What should be direction? You know positive is this way. Velocity it means to say this way. That R is this way. So if you apply the formula, what should be the direction?
Inwards.
Inverse, right? So this inverse is the direction. Make sense? Because why we are calling it to be the inverse is a direction? Because we are, if you see carefully, magnetic field is due to the current, and current you can say in two ways. What? Opposite of the electron, or in the direction of positive, because assume positive charges are there, right? There were no positive charges. So assume at this particular point you don't have any positive charge. It was a completely neutral body. Okay? Four things are there, they are neutral right now. What happens is, from here one electron moved and came here. Can I see you have generated a positive charge? You got one positive charge. After after a minute, another electron came out. You can will say this is positive. Basically, you are saying this positive is moving this side. You can say in this way. So what is the direction of it? You will say the direction of this is nothing but inside. Clear?
Yes.
Okay, that's okay. Now we are going to calculate the value. What is the angle between them? Call this as angle theta. Okay. So this assume because we are talking about very small length, because we are talking very small length, you can call this as very small dB, right? So what dB is directly proportional to? Directly proportional to the length. If I increase this length, I will have more value, right? Another is it is directly proportional to sine theta, as we have already stated, because the same thing is there, okay? 1 by r square. So what is the formula you are going to get? dB is equals to mu naught by 4 pi, okay, I times of dl sine theta. Okay? Keep it as ideal because more the current, more the why I'm saying this ideal because more look, if you increase I, it means you are increasing the flow of current, flow of the charge. It means more current, right? More charges means to say more value. DL basically more length part you are going to take, more value of the charges you are going to take. Okay, so this is why this ideal. Okay? So if you see carefully what we have get after that R square. This is what we have got. And again, I is a scalar quantity. What you can do is just multiply up and down with this. So you will be getting this thing. You can rewrite this thing as mu naught by 4 pi. Okay, I as it is. What you can say is instead of V, you know that this V and the DL they have same direction. So can I say that because right now we don't have any parameter of V, so you can simply call this as DL cross R vector divided by R cube. Clear? This is the value of magnetic field, small magnetic field due to this. And if you wanted to integrate, if you wanted to get the magnetic field due to the complete wire, you need to integrate it, okay, for all the values of length. Because if you reach here at this particular point, you will be having a different value of theta. Okay, this theta will be different. This theta is going to be very different. Understood my point? So you need to integrate in that case, and this R value is also going to be different. Is it clear now?
Yes, sir.
Okay. So that is the thing. This is a very key factor we have derived. This formula is going to be used in the rest of the chapter. Okay. So let's talk about this particular portion. I'll be going to take this portion. If you zoom that particular small portion, because I told currents are going upside, right? So what if you can say negative charges are there? They are going downside. We know that Kitna, when current is moving, electrons are moving away. So you have two ways. Either assume that positive charge is moving in the direction of magnet current and calculate the uh, field due to that charges. In another way, what you can do is you assume that this is charge, negative charge in going in this way, and you know the B has a negative direction. It means whatever the direction, magnetic field you are going to calculate due to this, that will be opposite sense, right? So this is the direction. Okay, this is the direction, and you know you wanted to calculate it over here. Okay. So what is the magnetic? What is the angle theta you are going to get this? This is the angle theta. Understand my point? Because the motion of charge is there. Because direction of current is this, but direction of charge is this. So this is theta you are. Is it clear now? Okay. You know,
Yes.
using the previous formula which we calculated in the last session, the dB was coming out to be mu naught by 4 pi. Okay. Multiplied by what?
Um,
Velocity cross r divided by r cube, and total was multiplied by the charge itself, right? So you can put charge over here or there, but I'll keep here. If you see it is a negative, right? This is minus c because why negative? Because of the value. Okay. So if you use this v cross r only, if you use v cross r, you are going to get upside, okay? Directly upside. But this negative will make the net current downside. Is it clear now?
yes, sir.
So what this comes out as, you can read as the same thing as this 4 pi v r by r cube this E, okay, the negative is outside, negative is outside, keep negative is outside. That is the thing. This is the exact value. Understood? But we can actually change the thing a little bit. What we can change, what is this velocity? Velocity, can I say that velocity is nothing but dl by dt, is it? And if I keep the value of this thing, can I say that this whole thing is coming out to be dl cross r divided by t?
Yes, sir.
Okay. So from here you can simply say whatever we have got, and you have e into multiplication. Now, if you see carefully, dl cross r divided by t, just remove this t. Okay. The moment you remove this t, what you are going to get is r cube as it is, and e divided by what is charged by time. Can I say that is the current itself? And that's what you have got over here, right?
Fine.
If you just finally put the things over here, mu naught by 4 pi. Okay, and one more thing. What is one more thing is this is minus e by t, right? Okay, we keep it as it is. This negative inside. This is minus e by t. Minus e has velocity in the downside direction. Okay, and we are going to keep it upside. In another ways, let's okay, just do it. Take as it is, whatever you want. E by t we have. Just think of it. Instead of e by t, I'm going to replace it with the I. And negative was there. So dl cross r times of divided by r cube, and I is there. Now you will say that our upper derived formula don't had any negative, but here I am having it. So this negative is due to the direction. Here I have taken the direction of this. But what is the direction of dl I have taken? The dl I have taken as the upper direction. Understood my point? I was saying my particle is going this velocity, but I took this dl and divided by the time. That's why I was getting. So what I need to do correct is instead here I was supposed to take where I shown you this thing. Yeah, here I was supposed to take minus 2. Is it clear now? So if I'm going to take this, you will be getting negative here, you will be getting negative here. This negative will make it positive. The final relation comes out as mu naught by 4 pi I as it is. Okay, sorry, I dl cross r divided by r. Is it clear now?
Yes, sir.
Okay, so this was the part. Okay, I'll remove the bottom part because I just wanted to show you how we had come up with that derivation directly. So you should be able to derive all these things by yourself. Okay? So what are the two key factors we have studied so far? Two formulas. So far. This is mu naught by 4 pi. Okay, charge v cross r divided by r. Which formula is this? Magnetic field due to moving charge. Okay? Moving charge. Things to be noted that B is perpendicular to V and B is perpendicular to R. This is the key thing to be noted. After this, what's the next? B is equals to mu naught by 4 pi. Okay. This is constant value, keep it outside as it is. Multiplied by the current. Instead of V, now you can keep DL into R divided by R. Another way is because this is a positive charge, you can what you can say is this I can be written as q by t. Okay, what is it? Q by t, and dl by t gives you velocity itself. Because the same things are same. If you divide if you want to open this v, it will become dl divided by time, and time by this thing comes r. These things are there. So you have to keep that in the mind. Magnetic field to current carrying wire. Okay, that is the important part to remember. Here also, B is perpendicular to the dl part which we are going to take. perpendicular to the eye because DL is generally in the direction of eye itself. What we are going to take is DL is the direction of eye, perpendicular to these three things are there. So yeah, that's all for the previous session. If you have any doubt, let me know. Otherwise, I'll end the session. Okay?
No doubts.
No doubt. Right? We can do session by this. So now I'll discuss pros and cons of this Biot Savart Law, what we are supposed to take care when we are using this. Okay? Clear?
Okay, sir.
Any
Yes, sir.
query?
No, sir.
Okay. Try to read the NCRT. First 3 to 4 pages. Please read that.
Okay,
All
sir.
right. So I'll end the session by this. Goodbye.